Hello chemists, this is Miss Placino and you are watching Screwcast 9.7 on Gibbs Free Energy. In today's lesson, we're going to talk about how to predict whether a reaction will be spontaneous or not. It's worth pointing out that when we use the word spontaneous in a chemistry class, we don't mean the same thing that you mean when you use spontaneous in an English class. If you're talking about somebody behaving spontaneously or making a spontaneous decision, you're usually talking about something being completely unprovoked or just kind of random or happening out of the blue. That is not what we mean in chemistry. When we're talking about spontaneous, we're talking about the release of energy. So we're looking to see whether a reaction is going to release or absorb energy. If it releases energy, it's what we call spontaneous. And if it absorbs energy, it's called non-spontaneous. You might be thinking, well, wait a second. No, we're talking about exothermic and endothermic here. Exothermic reactions release energy. Endothermic reactions absorb energy. What does spontaneity have to do with that? And this can be a little bit confusing at first for people. Gibbs Free Energy is talking about not just enthalpy, but entropy and enthalpy combined. So entropy is going to have an impact on whether a reaction occurs spontaneously or not. Don't stress out. We're going to talk about that in a lot of detail today and get you to predict whether reactions will be spontaneous or not based on just the idea of whether a reaction is exothermic, endothermic, increasing or decreasing in entropy. And we're going to do some calculations as well. All right, so let's get started. Let's talk about this example here, and you've got the same pictures in your notes. If I put a ball at the top of the ramp and I want to get it to the bottom of the ramp, what do I have to do? Well, hopefully this is a no-brainer. You give it a little bit of a push, and once you push it, the ball is going to roll down the ramp. If you think about your potential energy diagram, that little push that you have to give the ball, what does that most likely represent? Well, that's your activation energy, and every single reaction out there needs activation energy. Once activation energy has been provided, once I've nudged or pushed the ball, the rest of the reaction takes off and I don't have to do anything. I can kind of just sit back and watch. Ooh, let's think about the opposite situation. We've got the ball at the bottom of the ramp and we want to get it to the top. What do we have to do? Well, you're going to have to push it. So if I start to push it up the ramp or pull it up the ramp, I'll stop over there. What happens if I stop holding onto it? I stop pushing the ball. Well, it's going to slide back down. So if I take my finger off of it, it's going to fall back to the bottom of the ramp. If I want to get it all the way to the top of the ramp, I have to continue to provide energy. Push it up there. There you go. In order for a reaction to be spontaneous, it has to occur under conditions that result in an overall release of energy. The example of pushing the ball and getting it to roll down the ramp is a spontaneous reaction. The example where you have to try to get the ball to the top of the ramp is non-spontaneous. Pushing the ball down the ramp, activation energy is provided, the rest of the reaction occurs, overall release of energy. And a non-spontaneous reaction, I have to continuously provide energy or the reaction stops. Non-spontaneous reactions are possible. Some people who are new to chemistry make the assumption that, if it's not spontaneous, that must mean it does not occur. And that's not the case. There are plenty of non-spontaneous reactions that take place. The stipulation is you have to continuously provide energy in order for those reactions to occur. Right. So we're talking about reaction spontaneity. We're really looking at something called free energy. And free energy combines enthalpy and entropy. So we're looking at both delta H and delta S. We know that in nature, all substances, all chemicals are going to react in a manner that tends to lower the overall energy of the system. So if we think back to what we've talked about with enthalpy and entropy, let's do enthalpy first. Which one's going to lower the overall energy of a system? Well, we're talking about exothermic reactions. Negative delta H's are good or energetically favorable. Energetically favored, excuse me. As far as entropy is concerned, we know that nature is constantly moving to a more disordered state. Therefore, reactions that increase entropy are energetically favored. So if we have a reaction that is both exothermic and increasing in entropy, it should release a lot of energy. It should have a negative free energy value. We'll talk about how those are calculated. The change in free energy, and that's what we're going to be calculating, is looking at the difference between the change in enthalpy and the product of the temperature and the entropy change. And that's really just setting us up to use this formula. Delta G is free energy. It's the ultimate predictor of spontaneity. When delta G is negative, the reaction occurs spontaneously and energy is released. When delta G is positive, that means the reaction does not occur spontaneously. It means you have to constantly provide energy. Energy is absorbed. So we're going to look at both enthalpy and entropy, and temperature is going to play a role here. Temperature, in this case, has to be in Kelvin. You can imagine if we're using Celsius, it is possible for the temperature term to be negative. And since delta G is all about signs, it's negative, it's spontaneous. If it's positive, the reaction is non-spontaneous. We can't have negative numbers here. If you have a negative number or negative temperature value, it's going to kind of artificially change the sign of delta G, and we're not going to get the correct results. So we're going to use Kelvin so that we can completely avoid either having to multiply by 0 or having temperature be negative. Before we start putting numbers to this, I just want to think about this more conceptually. That formula back up here. Delta G is equal to delta H minus T delta S. If you think about it, delta H can be positive or negative, S can be positive or negative. Therefore, there are 4 possible combinations. We can have exothermic, both increasing and decreasing in entropy, and endothermic, increasing and decreasing in entropy. If you have an exothermic reaction that increases entropy, you have a negative delta H and a positive delta S. It doesn't matter what the value is for T. A negative number minus a positive number always gives you a negative result. And that means that reactions that are like reaction A, exothermic and increasing in entropy, are going to be spontaneous at all temperatures. If you look at letter B, we have exothermic, but decreasing in entropy. All of a sudden, we can't say with 100% certainty what the sign of delta G will be. Temperature plays a role here. If temperature is too high, you can end up with a very large value for T delta S, and it could be a negative minus a very big negative number and become positive. If temperature is very low, there's a good chance that this will stay a negative number, and high and low are relative terms. So if you have decreasing in entropy but still exothermic, you need low temperatures for spontaneous reactions. A good example is water freezing. If you put a bucket of water outside and it's negative 5 Celsius out, that's low enough where the water is going to freeze spontaneously. If you are endothermic, so positive delta H, and increasing in entropy, again, you can't say with 100% certainty what the sign of delta G will be. You need the T delta S term to be bigger than the delta H term, so this is going to be spontaneous at high temperatures only. Water boiling, for example. If you can get water up to a temperature over 100 degrees Celsius, even though it's requiring energy, it's going to boil spontaneously. And finally, in our last case, we have positive delta H, so endothermic and decreasing in entropy. This is always going to be a positive number, so this is never spontaneous. A good example is photosynthesis. It's always going to be, it requires sunlight, so no sun, no photosynthesis. It always requires energy. Let's do a couple of problems where we try to apply these concepts. So let's get to your practice problems. All right, in your workbook, you've got a whole bunch of practice problems that are asking you to balance an equation, predict the change in enthalpy, the change in entropy, and then determine when, if at all, this reaction can occur spontaneously. So let's walk through the first one together. Let's balance, because that's a good review of first semester topics. I've got carbon dioxide and water forming glucose and oxygen. So let's see, it's going to be 6, 1, 6. Okay, so I'm balanced. Trying to figure out whether this is exothermic or endothermic is pretty easy. We need to just look and see what side of the equation, reactants or products, the term heat is on. And then question number 1, heat is a reactant. So if heat is a reactant, that means heat needs to be absorbed as the reaction is progressing. And if heat is absorbed, that is endothermic. Positive. Okay. Delta S is a little bit more challenging to figure out. You're going to have to evaluate the change in entropy. So for question 1, I start off with 2 gaseous reactants, carbon dioxide and water vapor. I end up with a solid and a gas. I made a solid, so this definitely sounds like a decrease in entropy. If I think about the formula, delta G is equal to delta H minus T delta S. If delta H is positive and delta S is negative, this is always going to be a positive number regardless of the numerical values themselves. So delta G always is positive. That means that this is never at no temperature where this reaction occurs spontaneously. That's kind of the thought process here. Get it balanced, figure out what side of the equation heat is on and whether that makes it endo or exothermic. And then based on the reaction itself, do we have an increase or a decrease in entropy? And then think back to what the consequences are going to be from a sign perspective for delta G. So why don't you pause the video, try out questions 2 and 3, and we'll check them in just a moment. All right, so I've got number 2 balancing with 3, 2, 1, 6. Heat is on the product side, so I know this is an exothermic reaction, negative delta H. Delta S, I start off with 2 aqueous materials. I end up producing a solid and a liquid. That sounds like I'm decreasing in entropy. So if I've got a negative delta H and a negative delta S, in order for it to be spontaneous, this reaction needs to take place at low temperatures. For question 3, I've got 2, 1, 1, 1 as my coefficients. Heat is a product, so again, this is exothermic. And I start off with an aqueous solution, and then I produce aqueous, a gas, a liquid. So I think that's definitely an increase in entropy. If I'm exothermic and increasing in entropy, that's going to be spontaneous at any temperature. Temperature does not matter, does not impact the spontaneity of this reaction. Definitely worth your while to try out those other 4 on your own and check your answers against the key. One question that comes up from time to time when people are learning about Gibbs Free Energy is, what does it mean if delta G equals 0? I know if it's negative, it's spontaneous. If it's positive, it's non-spontaneous. Can it ever be equal to 0? And the answer is, yeah, it can absolutely be equal to 0. This means that the reaction is at equilibrium. This is a topic that we're going to get into more later this semester. But in order for a reaction to possibly exist at equilibrium, that reaction has to be reversible. So we have a forward reaction and we have a reverse reaction. So we can go from reactants to products, and at the same time, products can break back down and form the reactants. When delta G is equal to 0, that's telling us that the forward reaction and the reverse reaction are occurring at exactly the same rate. So if products are being formed just as quickly as they're breaking down, if you were able to see what was going on inside that reaction vessel and like take a picture and count up the number of reactant molecules and product molecules that were there, every time you took a picture, even though the reactions are still technically occurring, there is no net change. So we'd have a delta G equal to 0. Another common misconception is that the value of delta G is going to tell us something about how quickly this reaction occurs. Like you have something that's like really, really negative, like a delta G equal to negative 10,000 kilojoules per mole. That's going to be really, really fast compared to something that's just like negative 1 kilojoule per mole. That's not the case. Delta G has nothing to do with the speed. It's only telling us how much energy is going to be released or absorbed as we move from reactants to products. So don't fall into that trap. Okay, let's try to look at a real reaction instead of, not that the other ones were fake reactions. Let's look at one using thermochemical data instead of just trying to decide whether this is going to be positive or negative. So we've got some thermochemical data here. You've got your substances, You've got entropy values in joules per mole Kelvin. Who is beeping outside my apartment? You have heats of formation information in terms of kilojoules per mole. And you're set to try to find delta G. So this, I'm not going to lie, this is a lot of work to get through. So I'm going to get over to your practice problem so we can walk through this one together. Okay, we're back to the problem. So we're trying to calculate delta G for this reaction at 100 degrees Celsius, and we've got the thermochemical data in regards to the heats of formation and the entropy of our reactants and our product. Basically, we need to try to, so we know that in order to find delta G is equal to delta H minus T delta S. Okay. Think about what we know so far. I don't know delta G. I know that's what I'm trying to figure out. I don't know delta H, but I can calculate it. I know that temperature has been provided. It's 100 degrees Celsius. You know that has to be in Kelvin. And I don't know, I'm not provided with the change in entropy as we go from reactants to products, but again, I can calculate it. In class, what we ended up doing was kind of pairing you up with somebody calculate delta H, somebody else calculate delta S. And they're calculated in exactly the same way. Delta H of the reaction is equal to the summation of moles H products minus the summation of moles H reactants. Delta S of the reaction, it's exactly the same. Summation of moles entropy of the products minus the summation of moles entropy of the reactants. Now in lesson 9.4, we went through how to calculate delta H. So I don't want to spend a lot of time doing that. I want to make sure that we're trying to figure out how to use this delta G equals delta H minus T delta S formula. If you're a little shaky on how to use this formula right here, calculating the enthalpy of the reaction, go back to screencast 9.4 and watch. But I will tell you that for this reaction, enthalpy is equal to negative 2235.8 kilojoules per mole. Delta S is equal to negative 33.1 joules per mole Kelvin. Suddenly now I have information to fill in the rest of this equation. My delta H, myself a little bit more room, delta G is equal to negative 2235.8 kilojoules per mole. Be careful here. I've got joules per mole Kelvin for delta S. I have kilojoules per mole for delta H. I need to convert. So I'd have negative 331 kilojoules per mole Kelvin. From there, it's just really a matter of, again, plug and chug. I've got kilojoules per mole Kelvin times Kelvin, so the Kelvins will cancel out. I've got kilojoules per mole minus kilojoules per mole. So I can solve, put that over here, and I end up with a value of negative 2186 kilojoules per mole for delta G. If delta G is equal to negative 2186 kilojoules per mole, I know that this reaction must be spontaneous. There we go. So this is a lot of work, especially if you're just given S and delta H sub F values. You have to go through and calculate the change in enthalpy and the change in entropy of the reaction. Again, not real difficult to do, but definitely time consuming. It's also possible to calculate the delta G of a reaction using delta G. The delta G of the reaction is equal to summation N G of products minus summation moles G of reactants. I'm probably not going to ask you to do too much with that because you've used that formula or something strikingly similar to it so many times. But it can be solved for that way. The trick with your delta G, the Gibbs Free Energy equation, this one right here, is first off, making sure that you're working in Kelvin. You know I'm going to be a jerk, and I'm not going to give you a temperature in Kelvin. I'm going to give it to you in Celsius. So you know that in order to get from Celsius to Kelvin, you just have to add 273. And that'll give you a Kelvin temperature. The other little thing to watch out for is your units. We've got kilojoules per mole and we've got joules per mole Kelvin. Most people, by the time they get to this point, they're so excited that the problem is almost over that they get lazy, they don't put in their units, and then they make some careless mistakes. You need to convert out of joules into kilojoules or out of kilojoules into joules. And if you don't do that, you're going to get the question wrong. So I think the easiest thing to do is just take your change in entropy term and just move your decimal point 1, 2, 3 places to the left and get an answer, or a value I should say, in kilojoules per mole Kelvin. I gotta say, when I see people make mistakes, and it's not just careless typing things into their calculator mistakes, it always comes from, oop, I forgot to convert the temperature, or oops, I forgot to convert out of joules into kilojoules. This is some advanced stuff. This is more like AP chemistry stuff, but you are more than capable of handling it. You've got the math skills. Hopefully now you feel a little bit more comfortable about what delta G is telling you as far as what the sign means, and the relationship to spontaneity and energy. And try these problems out. They can get pretty challenging, especially, I think it's question B. It's non-spontaneous, and then you can see if you can figure out what temperature the reaction actually does become spontaneous. So definitely try out question B, check the answer key online, and make sure that you've got the hang of this. All right, guys, that's it for today. Sorry this one was a little bit long. Thanks for tuning in, and I hope you found this helpful.